Hello and welcome back to Chapter 2. Today we're going to look at complex numbers in Section 2.4. Up until this point, we've learned that some quadratic equations have no real solutions. For instance, and you don't have to worry about writing this down, but if I give you something like x squared plus 1 equals 0 and ask you to solve it, you would tell me that x squared equals a negative 1 and that you can't go ahead and complete this because you can't take the square root of a negative 1. And up until this point, I would agree with you. However, now we're going to look at what we call complex numbers. And within complex numbers, we're going to be able to define the square root of a negative 1 with what we call the imaginary unit. And the imaginary unit is shown as an I. Okay, and this does represent the square root of a negative 1. Now, if we take and we square this, so if I square I squared, and I square the square root of a negative 1 squared, that's going to give me I squared equals a negative 1. So you do have to know both of these right here. Now, complex numbers are going to be when we take a real number and pair it, usually like we're adding it or subtracting it, something like that, with an imaginary unit. So something like that would be this a plus bi. Now a plus bi is what we call standard form, okay, and the a will be the real number, and then this piece here is actually the complex piece, or the imaginary part. And in order for us to decipher whether or not two complex numbers are equal, so I'm going to look at something like this. If I say a plus bi equals c plus di, I know that the corresponding parts have to be the same. So in other words, remember IFF is really if and only if. If a is equal to c, so this term here is the same as this one, and b is equal to d, then these two are equivalent complex numbers. If one of them are different, then it's not going to go. And if you're writing this down, I don't know why that B showed up there, so you can go ahead and cross that out. Now we can go ahead and perform operations with complex numbers. If we're looking at addition or subtraction, let's say we're going a plus bi, and we want to add that to, or subtract it, it doesn't matter, c plus di, we're going to essentially add the like parts, or we're going to add the real parts together, and then we're going to add the complex pieces together, or imaginary pieces. So I'm going to end up with the sum, or difference, of a plus c, and then I'm going to add that to b plus d, and all of that is going to be attached with the imaginary piece, or I. Now when we're doing multiplication, we actually have to do the distributive property, and I want to show you that with an example here in just a minute. So let's look at some examples where we're adding or subtracting complex numbers. So part A, we're going to add 7 plus 3i to 5 minus 4i. So we're going to add our real parts. So 7 plus 5 will give me 12. And then I'm going to add the complex parts, or imaginary parts, and say 3 plus a negative 4 is going to be minus I. So this here would be my final answer. Likewise, for part B, I have 3, and that's really minus 5. So that's going to give me a negative 2. And 4 minus a negative 2, so this is going to be distributed, that becomes 4 plus 2i, so I end up with plus 6i. In part C, I'm going to add all of my real pieces together. So I have, this is going to give me a positive 3 plus 2, or 5. Then for my imaginary pieces, I have 4 minus 5i, because I'm going to distribute that. So 4 minus 5i gives me a negative I, plus a negative 6i gives me a negative 7i. In my last part, or part D, I'll do just what we've done in the previous examples. add up my reals, so I have 5 plus 3 is 8, minus 8 is 0, so we have 0 plus, then negative I plus 4i is 3i, minus 3i, because I'm going to distribute that, gives me 0 as well, so the whole thing is going to give me 0. Now for example 2, we want to go ahead and distribute. Like I mentioned earlier, we're going to use the distributive property. So I'm going to take 8i and multiply it by the 4. So that's going to give me 32i. Now I have 8i times a negative 3. So this is a negative 24i squared. Now the thing with complex numbers that we have to remember is anytime you have an I squared or an I to an even power, that's really going to give us a negative 1. And that's because I squared equals negative 1. And if you don't remember that, go back and look at one of the first couple of slides that we did. So to simplify this, that tells me that this right here is really going to turn into a negative 1. So now I have a negative 24 times a negative 1, which is going to give me a positive 24 plus my 32i. So this right here is your final answer for part A. Now for part B, I'm going to do the same thing. I'm going to go and distribute. So I have 3 times 5, which is 15. 3 times 4i will give me a plus 12i. Negative I times 5 is minus 5i. And then I have negative I times a positive 4i will give me minus 4i squared. So let's combine our like terms. So this gives us 15 plus 7i minus 4i squared. Well, remember, I squared is really a negative 1. So I have negative 4 times a negative 1, which is going to make this a plus 4. So now I have 15 plus 4, or 19, plus 7i. Now we'll go ahead and do something very similar to that in part C. So for part C, we're going to take our 2's and multiply them together to give us 4. 2 times a negative 4i will give me a negative 8i. 4i times 2 will give me plus 8i. And then I have 4i times a negative 4i will give me a negative 16i squared. And remember, I squared is going to give us a negative 1. So negative 16 times a negative 1 is really a positive 16. Plus 4 will give us 20. And negative 8i plus 8i is 0. So my final answer then will be just 20. And that makes sense because if you remember, our middle term when I have the same first and second term, but I just differ by the signs, that's going to cancel out that middle term there. And then last but not least, we have part D. This is 5 minus 3i, the quantity squared. Please make sure that you know that that's really 5 minus 3i times 5 minus 3i. So now when we FOIL this, we're going to be left with 25 minus 15i minus 15i plus 9i squared. And if we simplify that down, our middle terms here are going to simplify down to a negative 30i, and I'll rewrite that here in a second. So that gives us 25 minus 30i plus 9i squared. I squared is going to go to a negative 1. So I really have 25 plus a negative 9, or 25 minus 9, which will give me 16 minus 30i. Now back on the previous example, if you remember what part C said, part C gave us that we had 2 plus 4i times 2 minus 4i. These are what we call complex conjugates. And they're called complex conjugates because your real terms are the same. Both of them have a 2. The imaginary pieces are the same with the 4i. They just differ by the plus and the minus. So a complex conjugate will give you the same real terms, the same imaginary terms, but they differ by the plus and the minus in the middle. And this is useful because sometimes, like as you'll see here in a second, once we multiply these two together, we're actually going to cancel out that middle term, which gives us the imaginary piece, and our final product then will consist of just a real number. And example 3 is going to show us just that. So we have 5 minus 4i, and we're going to multiply it by its complex conjugate. Well, that's got to be 5 plus 4i. So now when we multiply these together, we're left with 25 plus 20i minus 20i minus 16i squared. Well, if you notice, I have a plus 20 and a minus 20i in the middle, so these are going to cancel, and that's going to leave me with 25 minus 16i squared. Well, the I squared term is going to go to a negative 1. Negative 1 times a negative 1 will make that a positive, and 25 plus 16 is going to give me 41. So you say, when are we going to ever use that? And I'll tell you, we're going to use that here in example 4. Example 4 says to write the quotient in standard form. Now the thing with the quotient is we don't want a complex number in our denominator. So the only way we can get rid of a complex number is to multiply it by its complex conjugate. So in other words, we need to multiply this fraction right here by the complex conjugate of the denominator in order to get that to cancel. So I'm going to multiply this by, and the complex conjugate of the denominator is 2 plus I, and I have to multiply both the numerator and the denominator by that so that I'm really multiplying by 1. Now I'm really multiplying two fractions. So in the numerator, I have a standard foiling problem. So this is going to give me 4 plus 2i, then I have another 2i, and then a plus I squared. And we're going to do the same thing in the denominator. So now I have 2 times 2 is going to give me 4 plus 2i minus 2i minus I squared. So when I simplify now, I'm left with 4 plus 4i plus I squared divided by 4. Now my positive 2i and negative 2i are going to cancel, so then I'm left with minus I squared. Again, I need to further simplify this. I squared will give me negative 1. I squared here will give me a negative 1. So in my numerator, I'm left with 4, or this 4, and this negative 1, which will give me 3 plus 4i divided by 4 minus a negative 1 will give me plus 1, or 5. Now, this right here is a complex number, yes, but it tells me to write it in standard form. Well, standard form, I need to separate the real piece from the imaginary piece. So to do that, I'm going to be left with 3/5 for my real part plus 4/5 I as my imaginary part. So this right here is actually your final answer. The last thing we're going to look at when dealing with complex numbers is what we call the principal square root. And back in Algebra 2, I know you talked about this. But a principal square root is something like the scenario here, where you're given the square root of a negative number. And I hope you remember that you can't take the square root of a negative number. So what we need to do is we need to put it in a format where we can actually go ahead and do something with that. So the principal square root then would be where we take out and factor that negative 1 out. And remember, negative 1, the square root of a negative 1 is I. So I'm going to factor an I out and then just take the square root of a. Now I can do that because this is really the square root of a negative 1 times a. And if you recall, you can actually break that down into the square root of a negative 1 times the square root of a. Well, the square root of a negative 1 now is I, and I'm left then with the square root of a. So that's kind of like the behind the scenes work that's being done. So let's go ahead and look at some examples of how we're going to handle or deal with this. So example 5 says to write the complex number in standard form. So the first thing we're going to do is we're going to rewrite this as I times the square root of 14 times I times the square root of 12. All I've done is I've pulled the negative 1 out, and I've done that with an I, because the square root of a negative 1 is I. So now I have I times I, which is I squared, times the square root of, and you can do 14 times 12, which gives us 168. So now I can rewrite this because of that I squared. I know that I squared is really a negative 1 times the square root of 168. And you can go and further reduce that square root of 168 if you'd like, or you can leave it like that. Now for part B, I'm going to rewrite these as I times the square root of 27 minus I times the square root of 12. Now, I have two terms with i's, and I should be able to add them as long as the number underneath the radical is the same. So I cannot add them as they currently stand. But I can rewrite the radicals, and by doing that I can break this apart. I can rewrite this as I times the square root of 3 times 9 minus I times the square root of 3 times 4. So if I simplify those radicals, that's going to give me the square root of 3. I can't simplify, but I can simplify the square root of 9. So I end up with 3i times the square root of 3 minus the square root of 4 is 2. So I have 2i times the square root of 3. Now I have the same number underneath my radicals. So all I have to do is add or subtract the coefficient. So this is going to give me 3i minus 2i is 1i times the square root of 3. So this right here then is my final answer. And last but not least, we have a negative 2 plus the square root of a negative 5, and we're going to square that whole quantity. So the first thing we're going to do is we are going to want to rewrite this negative 2 plus, and it will become I square roots of 5. And when we square it, I'm going to rewrite it as negative 2 plus I square roots of 5. So we're going to make it a product of two binomials, and now we're just going to FOIL. Negative 2 times negative 2 is 4. Negative 2 times I square roots of 5 gives me a negative 2I square roots of 5. Then I have I square roots of 5 times a negative 2, so I have minus 2I square roots of 5 plus, because I have a plus and a plus, and I times I is going to give me I squared. Square root of 5 times 5 will give me 5. So now if I simplify, I'm left with 4 minus 4 square roots, or I'm sorry, 4i times the square root of 5. Then I have plus, but this I squared is really going to give me a minus 1, and negative 1 times 5 is really a negative 5. So I can further simplify that to 4 minus 5, which is negative 1, minus 4i times the square root of 5. And this would be your final answer. And our last example for section 2.4 is example 6. Example 6 says to solve the quadratic function 7x squared plus 5x plus 2 equals 0. This is something that you cannot factor. You can try, but it's not going to factor nicely with a coefficient of 7 and a constant of 2. So let's go ahead and use the quadratic formula. quadratic formula, for those of you that don't remember, is the opposite of b plus or minus the square root of b squared minus 4ac divided by 2 times a, and that's x equals. So our b value, that's going to give me the opposite of 5, which is a negative 5, plus or minus the square root of 5 squared minus 4 times a, which is 7, times c, which is 2. We're going to divide the whole thing by 2 times 7. So we end up with a negative 5 plus or minus the square root of 25 minus 56 divided by 14. So now if we go and simplify that, we have a negative 5 plus or minus the square root of 31, and that's a negative 31 divided by 14. Well, now we just ran into an issue. I can't take the square root of a negative number, but because of complex numbers, I know that I can rewrite that as a negative 5 plus or minus I times the square root of 31 divided by 14. And if I simplify this into my complex in real parts, this gives me a negative 5/14 plus or minus I times the square root of 31 divided by 14. And this right here would be my two imaginary solutions to this function here. So with that, have a good night, and I will see you guys tomorrow.